welcome to this problem walkthrough. Today, we'll explore problem number 1220, Count Vowels Permutation, a fascinating challenge that combines dynamic programming with combinatorics. Let's dive in and break it down step by step. In this problem, we're tasked with counting all possible strings of length and that consist only of vowels. The vowels are a, e, I, o, and u. However, there are specific rules that govern how vowels can follow each other. For example, a can only be followed by e, while e can be followed by either a or I. Similarly, I has more flexibility and can be followed by a, e, o, or u. O can transition to I or u, and finally, u can only be followed by a. The goal is to count all valid strings that satisfy these transition rules for a given length n. To ensure the result fits within computational limits, we return the count modulo 10 to the power of 9 plus 7. The input is a single integer n, representing the string length, and the output is the total number of valid strings for that length. The output is an integer, representing the total number of valid strings of length n, computed modulo 10 to the power of 9 plus 7. Let's look at some examples to better understand the problem. For n equals 1, the output is 5. This is because, with a string length of 1, each vowel forms a valid string by itself. So the valid strings are a, e, I, o, and u. Each of these satisfies the transition rules since there are no other characters to follow them. Now, for n equals 2, the output is 10. This is because we now consider all valid transitions between vowels. For instance, if the string starts with a, the only valid string is ae. If it starts with e, the valid strings are ea and ei. Starting with I provides the most flexibility, allowing strings like ia, ie, io, and iu. From o, we can form oi and ou, while u allows only ua. Adding these combinations gives us a total of 10 valid strings. For n equals 5, the number of valid strings increases significantly, and the total comes out to 68. Here, the transitions become more complex as we chain together multiple valid pairs according to the rules. The calculation involves systematically extending valid strings of length 4 to length 5 while ensuring every transition adheres to the given rules. By following this process, we find that there are exactly 68 valid strings of length 5. To solve this problem efficiently, we must consider the constraints. With n going up to 2*10⁻4, directly generating and counting all possible strings isn't feasible. Instead, we use dynamic programming to calculate the result efficiently. This approach allows us to compute the number of valid strings for any length n by building on results for smaller lengths. Additionally, to handle the large output values, we ensure the result is always computed modulo 10 to the power of 9 plus 7. This avoids overflow and meets the problem's requirements. By applying these techniques, we can handle both small and large inputs efficiently. To solve the problem, one approach we could consider is a brute force method, where we recursively generate all possible strings of length n that adhere to the given vowel transition rules. The idea is straightforward. At each position in the string, we explore every valid vowel transition recursively. The base case would simply return 1 when the desired string length is reached, and the recursive case would sum up the results of all valid transitions. However, there are some critical observations about this approach. Since every position in the string depends on the vowel used in the previous position, and there are 5 possible vowels, the number of states grows exponentially. For example, for a string of length n, the time complexity would be 5 to the power of n, which becomes computationally impractical for large values of n. While this approach is conceptually simple, it results in excessive computation and is thus unsuitable for larger inputs, such as when n is 10,000. To address these inefficiencies, we turn to dynamic programming. Using a dynamic programming approach, we can significantly optimize the solution by framing the problem as a state transition process. Here, each vowel represents a state, and we calculate the number of ways to transition to each state based on the rules provided. For instance, the vowel a can only transition to e, while e can transition to both at and I, and so on. To formalize this, we define dp, I, v, as the number of strings of length I that end with vowel v. The transition rules are then captured in mathematical formulas, such as dp, I, a, equals dp, I1, e, plus dp, I1, I, plus dp, I1, u, which accounts for all the vowels that can transition to at step I. Similarly, we compute transitions for the other vowels using their respective rules. By summing up the values of dp, n, a, dp, n, e, dp, n, I, dp, n, o, and dp, n, u, we obtain the total number of valid strings of length n. This approach prevents recalculating overlapping subproblems and dramatically reduces computation time, making it efficient for large inputs. With a time complexity of O, n, and a space complexity of O, n *5, for the dp table, this method is already a significant improvement over the brute force approach. To further optimize space usage, we can implement a space-efficient version of the dynamic programming solution by using rolling arrays. Instead of storing the entire dp table, we only keep track of the previous state and the current state as we iterate through the transitions. This is done using two arrays, previous to represent the counts for vowels at step I1, and cur to compute the counts for the current step I. After calculating cur based on the transition rules, we simply update previous to hold the values of cur for the next iteration. At the end of the process, the total number of valid strings is obtained by summing the values in previous. This approach retains the same time complexity of O, n, while reducing space complexity to O, 1, since we no longer need to store the full dp table. This space-optimized dp strategy is the best choice for solving the problem. It is efficient, scalable to large values of n, and straightforward to implement, making it highly suitable for both competitive programming and real-world applications where memory and time are critical constraints. To start, our goal is to count the number of valid strings of length n that can be formed using the vowels a, e, I, o, u, following specific transition rules. For example, a can only be followed by e can only transition to a or I, and so on. A brute force approach to this problem involves generating all possible strings of length n and checking if they meet these rules. However, this would be computationally expensive, so we need a more systematic method. A recursive approach can be defined where we use a function dfs, current_char, length_remaining, that calculates the number of valid strings starting with a particular vowel and a given remaining length. The base case is straightforward. If we only need a string of length 1, any single vowel would suffice. For longer strings, we recursively explore all valid transitions from the current vowel, reducing the length by 1 in each step. Now, to implement this recursive approach, we start by calling the dfs function for each of the vowels with the initial string length n. For every call, we explore all possible valid transitions for the current vowel and sum up the results from these recursive calls. To optimize this process, we use memoization. A memoization table, memo, current_char, length_remaining, is used to store the results of subproblems so that we don't recalculate them. Before making a recursive call, we check whether the result for the current vowel and remaining length is already in the table. If it is, we simply reuse that value. By summing the results of all recursive calls for each starting vowel, we get the total number of valid strings. Additionally, we handle edge cases, such as when n is 0, by returning 0 immediately since no strings can be formed. This recursive strategy, combined with memoization, captures the essence of dynamic programming by breaking the problem into overlapping subproblems. The transition rules play a crucial role in reducing the computational complexity of the problem. Since only certain transitions are allowed between vowels, the search space is significantly smaller than generating all possible strings of length n. To implement this, we use a memoization table represented as a 2D array, memo, vowel, length, which stores the result for each pair of a vowel and a remaining length. This ensures that each subproblem is computed only once. Additionally, the recursion stack keeps track of the function calls. The depth of the stack corresponds to the length of the string, n. The pseudocode outlines the implementation. We start by defining the transition rules for each vowel. For example, a transitions to e can transition to a or I, and so on. Then, we initialize the memoization table and define the recursive function dfs. At this point, the pseudocode sets the foundation for the algorithm. The dfs function is the heart of this algorithm. It takes the current vowel and the remaining length as input. If the remaining length is 1, we return 1 because any single vowel forms a valid string. Before proceeding with recursive calls, we check if the result for the current state is already in the memoization table. If it is, we return that value directly, avoiding redundant calculations. Otherwise, we iterate over all valid transitions for the current vowel, making recursive calls for each valid next vowel while reducing the remaining length by 1. The results of these recursive calls are accumulated to get the total count for the current state. This total is then stored in the memoization table for future reference. Finally, to compute the total number of valid strings, we iterate over all vowels, calling the DFS function for each vowel with the initial string length n, and summing up the results. This approach ensures efficient computation by leveraging both recursion and memoization. Analyzing the complexity of this algorithm, the time complexity is O, n*5, where n is the length of the string and 5 represents the number of vowels. Each unique state defined by a pair of a vowel and a remaining length is computed at most once, thanks to memoization. The space complexity is O, n*5, for the memoization table, and the recursion stack requires O, n, space. These optimizations make the algorithm significantly faster than a brute force approach. Memoization reduces redundant calculations, while pruning ensures that only valid transitions are considered, minimizing the branching factor. Edge cases, such as when n is 0, are handled explicitly to ensure correctness. For an example, if n is 2, and given the transition rules, valid strings include combinations like a, ea, ei, ia, and others. The output would be the total count of these valid strings. This approach elegantly combines recursive exploration, dynamic programming, and careful optimization to solve the problem efficiently. This code solves LeetCode problem number 1220, count vowels permutation, by implementing a dynamic programming approach. The task is to count all valid strings of length n formed using vowels a, e, I, o, u, following specific transition rules. The function count vowel permutation begins by defining the modulo constant mod as 10 to the power of 9 plus 7 to prevent integer overflow during calculations. It initializes the counts for single character strings, where each vowel has one valid occurrence, a, e, I, o, u equals 1, 1, 1, 1, 1. The algorithm iteratively calculates the counts for strings of increasing lengths from 2 to n. During each iteration, it computes new counts for each vowel based on the given transition rules. A can follow e, I, or u. E can follow a or I. I can follow e or o. O can follow I. U can follow I or o. These rules are implemented using modular arithmetic to ensure that values remain within the bounds of mod. After computing the new counts, the old counts are updated to reflect the current state. Finally, the function returns the total number of valid strings of length n by summing the counts for all vowels, a plus e plus I plus o plus u, modulo mod. This approach is both time and space efficient, with a time complexity of O, n, and a constant space complexity, as it only keeps track of the counts for the current and previous iterations. This is the Java implementation of the count vowels permutation problem from LeetCode. The code mirrors the same logic as the provided Python solution, with key differences including type declarations and the use of Java's long type to handle large numbers. The algorithm uses dynamic programming to calculate the number of strings of length n ending with each vowel, adhering to the rules of valid transitions. The result is computed modulo 10 to the power of 9 plus 7 to handle large values. To solve the problem of counting vowel permutations, we start with an example where n equals 2. The task is to determine the number of valid strings of length 2 that can be formed by following the given set of rules. The vowels involved are e, I, o, and u. Each vowel can only be followed by certain other vowels as specified. A can be followed by e, I, or u, e by or I by e or o by I, and u by I or o. Initially, we assume that there is exactly one single character string for each vowel. This means we start with counts of 1 for each vowel, a, e, I, o, and u all equal 1. This setup forms the basis for calculating the possible permutations for larger string lengths. When calculating the permutations for strings of length 2, we use the given rules to determine how the vowels can transition. Starting with the initial counts of 1 for each vowel, we compute the new counts. Nu underscore a is the sum of e, I, and u, giving us 3. Nu underscore e is the sum of a and I, which equals 2. Nu underscore I is the sum of e and o, also resulting in 2. Nu underscore o is simply I, so it remains 1. Finally, nu underscore u is the sum of I and o, giving 2. These new counts are then used to update the values for the next iteration, so it becomes 3, E becomes 2, I becomes 2, O becomes 1, and U becomes 2. To find the total permutations for n equals 2, we sum up all these values, 3 plus 2 plus 2 plus 1 plus 2, giving us 10. Thus, the result for n equals 2 is 10. Next, we extend the problem to strings of length 3. Using the same rules, we begin with the initial state where the counts for each vowel are all 1. In the first iteration, which corresponds to length 2, we calculate new counts just as before, new underscore a equals 3, new underscore e equals 2, new underscore I equals 2, new underscore o equals 1, and new underscore u equals 2. These values are then used to update the counts for the next length. So now, A becomes 3, E becomes 2, I becomes 2, O becomes 1, and U becomes 2. This updated state sets the stage for calculating the permutations of length 3. For the second iteration, corresponding to strings of length 3, we again apply the rules to calculate the new counts. New underscore a is the sum of e, I, and u, giving us 6. New underscore e is the sum of a and I, which equals 5. New underscore I is the sum of e and o, resulting in 3. New underscore o is simply I, so it equals 2. New underscore u is the sum of I and o, which equals 4. With these updated values, A becomes 6, E becomes 5, I becomes 3, O becomes 2, and U becomes 4. Adding these together gives us the total permutations for n equals 3, 6 plus 5 plus 3 plus 2 plus 4, which equals 20. Thus, the result for n equals 3 is 20. Now we tackle the case where n equals 4. We start again with the initial state where each vowel has a count of 1. For the first iteration, corresponding to strings of length 2, we calculate the new counts, new underscore a equals 3, new underscore e equals 2, new underscore I equals 2, new underscore o equals 1, and new underscore u equals 2. These values update the counts, A becomes 3, E becomes 2, I becomes 2, O becomes 1, and U becomes 2. Moving to the second iteration, which corresponds to length 3, we calculate, new underscore a equals 6, new underscore e equals 5, new underscore I equals 3, new underscore o equals 2, and new underscore u equals 4. These updated counts are now A equals 6, E equals 5, I equals 3, O equals 2, and U equals 4, setting the stage for the final iteration. In the third iteration, for strings of length 4, we calculate the new counts using the same rules. New underscore a is the sum of e, I, and u, resulting in 12. New underscore e is the sum of a and I, which equals 9. New underscore I is the sum of e and o, giving 7. New underscore o is simply I, so it equals 3. New underscore u is the sum of I and o, which equals 5. With these updated values, A becomes 12, E becomes 9, I becomes 7, O becomes 3, and U becomes 5. Adding these together gives the total permutations for n equals 412 plus 9 plus 7 plus 3 plus 5, resulting in 36. Therefore, the result for n equals 4 is 36. The time complexity of the given solution is O, n, and here's how we arrive at that. First, in the initialization step, we assign initial values to the variables representing the counts of strings ending in each vowel a, e, I, o, and u. Since this involves setting a fixed number of variables, it takes constant time, which we denote as O1. Next, during the main loop, we iterate from 2 to n, performing a total of n1 iterations. Within each iteration, we compute the new values for the vowel counts based on the rules. Each of these calculations involves simple addition and modular arithmetic, both of which are constant time operations. Since there are 5 vowels, the updates for all of them in a single iteration still take O1. Multiplying this by the number of iterations, the total time spent in the loop is O(n). Finally, after the loop, we compute the sum of the counts of all vowels modulo 10 to the power of 9 plus 7, which is another constant time operation. Adding these together, the overall time complexity so far is O1 plus O(n) plus O1. Combining all the steps we discussed, the overall time complexity of the solution simplifies to O(n). Now, let's analyze the space complexity. The solution uses 5 variables a, e, I, o, and u to store the counts of valid strings ending with each vowel. These variables require a constant amount of memory, regardless of the input size n. Additionally, the algorithm does not use any data structures such as arrays or matrices that grow with the input size. Temporary variables like new_a, new_e, new_i, new_o, and new_u are used during each iteration to compute the next state, but these are also fixed in size and do not depend on n. Because the memory usage does not scale with the input, the total space complexity is O(1). With the space usage being constant, the overall space complexity remains O(1). Now, let's compare this dynamic programming solution to a brute force approach. In a brute force method, we would generate all possible strings of length n and then verify each string against the vowel permutation rules. This approach results in exponential time complexity. Specifically, since each character in the string has 5 vowel options, there would be a total of 5 to the power of n possible strings. Verifying each string for validity takes O(n), leading to a total time complexity of O(5 to the power of n*n). This quickly becomes computationally infeasible as n grows larger. On the other hand, the dynamic programming solution avoids generating and validating all possible strings. By focusing only on the counts of valid strings ending in each vowel, the problem is reduced to a linear time complexity of O(n). This significant optimization is achieved by iteratively applying the rules to update the counts, making the solution far more efficient. The optimality of this solution lies in its space-efficient dynamic programming approach. Instead of maintaining a full DP table to track all states, we only store the current and next states for the vowel counts. This optimization reduces the space requirement from O(n) to O(1), as we no longer need memory that scales with the input size. Meanwhile, the linear time complexity is unavoidable because we must process each length from 2 to n to compute the final result. Thus, the solution achieves both time and space optimality. Compared to the brute force approach, this method is exponentially faster and uses minimal memory, making it highly efficient and well suited for solving this problem at large input sizes. One of the most common mistakes when solving the count vowels permutation problem is misunderstanding the transition rules between vowels. Each vowel can only follow certain others, based on the constraints. For instance, you can only come after O or I. If you misapply these rules, your solution will generate invalid sequences and fail to meet the problem's requirements. Another frequent issue arises in recursive solutions without memoization. Naively recalculating overlapping subproblems leads to a significant increase in runtime. The solution here is to use memoization to store the results of these subproblems, ensuring you avoid redundant calculations. Additionally, many people overlook edge cases and base cases, such as when n equals 1 or when n is very large, like 10 to the power of 4. Failing to handle these can lead to runtime errors or inefficiencies. Lastly, brute force methods, which attempt to generate all possible strings, are highly inefficient. Because the number of strings grows exponentially with n, this approach quickly becomes computationally infeasible for larger values of n. Incorrectly calculating the modulo is another potential pitfall, especially in problems involving large numbers. If you forget to apply the modulo operation at every step or apply it inconsistently, you risk encountering overflow or incorrect results. To avoid this, always ensure the modulo is applied consistently throughout intermediate calculations. Now, when preparing for interviews, keep in mind that this problem is essentially dynamic programming on a graph. Here, the vowels represent states, and the valid transitions between them form edges. Recognizing this structure can help you model the problem effectively. Interviewers often expect you to explain this and identify the need for an optimized solution, particularly given constraints like n being very large. An O, n, or O, k *n solution, where k is the number of vowels, is typically the target. Be prepared to compare naive approaches, such as recursion or brute force, with more efficient ones like dynamic programming or matrix exponentiation. Additionally, if you're using dynamic programming, consider optimizing space complexity. Instead of maintaining an O, an *k table, you can reduce it to O, k, by reusing values from previous states. There are several related problems that can help you understand the count vowels permutation problem better. For instance, LeetCode 70, the climbing stairs problem, is a classic example of dynamic programming with overlapping subproblems. Similarly, LeetCode 509, the Fibonacci number problem, involves a simple recurrence relation that can be optimized for both time and space. Another similar problem is LeetCode 935, the night dialer, which shares a similar structure where transitions between states, in this case, digits, are constrained. Of course, LeetCode 1220 itself is directly related, offering a chance to practice working with constraints and transitions. Now, when it comes to alternative approaches, dynamic programming is a straightforward and efficient choice. By defining dp, I, j, as the number of valid strings of length I ending with the jth vowel, you can solve the problem in O, and *k, time and space. For a more advanced approach, matrix exponentiation allows you to represent transitions as a matrix and compute its nth power in O, log n, time. This is particularly useful for very large values of n, though it can be challenging to implement during an interview. Finally, recursive backtracking with memoization, while less efficient, is an intuitive way to grasp the problem structure, even if it's not practical for large constraints. When tackling this problem in an interview, one of the most important steps is to write down the transition rules explicitly. This prevents mistakes and ensures you adhere to the constraints. Begin by explaining a brute force approach to demonstrate your understanding of the problem, even if it's not the most efficient solution. From there, you can discuss how to optimize it. Be sure to clearly articulate the time and space complexity of each approach you propose. This not only shows your technical understanding but also helps the interviewer see your thought process as you refine your solution. By following these steps, you'll present a thorough and well-structured approach to solving the problem. Great job! We tackled the problem using an efficient dynamic programming approach and highlighted some key strategies for optimization. Remember to practice similar problems to strengthen your skills further. Thanks for joining, and we'll see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!